I'm an iOS developer at this point. I've been writing iOS apps since 2009. So it was only a year since the App Store was introduced. And before that, I've been a Java enterprise web developer for 8 years. Thank you. So in the past, I've done a lot of servlets and your typical struts if you're a Java developer, Hibernate, JPO stuff. And quite recently as in 8 years now that I think of it, I've been doing iOS. And I've built apps like banking apps, just to give you an idea. I've built travel apps. I've built social apps, let's say, take a photo, have a feed, have a news feed. Just to give you a bit of a context of what I'll be talking about and how does this relate in practice and where my experience comes from. So I guess the first question is, why should you do it? I guess if you're not doing it, it's like you're running blind. It's like being on stage here and walking with your eyes closed. Let's try this. Am I going right? And then all of a sudden you trip over because you really have no sense of how things are, where you're heading, because you haven't bothered checking. You haven't bothered to look first before you start walking down that path. So you should really put it in your routine as part of developing code to do profiling. And it will become more clear as I go over the slides. The way you do CPU and time and memory profiling is you look for red flags. It's not a binary thing. You cannot just say, just because CPU is high, that means it's bad. Or just because memory usage is high, that means it's bad. It is an indication. And it takes a bit of experience, let's say. But you also need to look for heuristics. So you look for patterns. You look for things that don't make sense. And typically, you would do it on every new functionality that you add, or on every release, at the very least. The reason should be obvious. If by doing it on every functionality, on every new functionality, you have a very clear sense of what the state of your CPU and memory usage is at each time, at each step of the way. So let's say you're working on a news app and you have a feed and you've built that. You would profile that at the very end of building this feature because that gives you an overview of how this feature compares and how this feature measures in terms of CPU and memory. So the next time, when you do your profiling for the next feature, let's say the user's profile, you know whether memory usage has regressed from the first time, so whether it was good and now it's bad, simply speaking, or how much each of your features is contributing to the problem that you see. So it's a good idea to do this on every functionality and group functionality together. Obviously, you need to do this before you release it to your users because it's not any good after that. It helps if you have some knowledge of the code base. It makes things easier because obviously you can look through stuff and you know where to look, but it's not necessary, it's not required. And again, it will become clear why that's not the case. You can still do it without having any inside knowledge. You should still be able to jump on a new unknown source code and do it. Having deep knowledge of the iOS SDK is more important, actually. You need to know how Grand Central Dispatch works and how memory management works. If you don't know this, then you will probably have a hard time grasping the concepts that you need to look for, and what triggers this behavior that you see with usage. So my first question is, how many of you are you familiar with ARC and memory management? Okay. And how many of you are familiar with Grand Central Dispatch? Okay. So the first thing is to prepare. And how do you prepare? Typically, you would do it on a device. The reason for this is if you do it on a device, then obviously you get more real-world conditions, let's say, of your app, and how it performs. For some things, it's not critical, but I would say just to be safe, and especially if you're a beginner, start with a device rather than on the simulator. The other thing you need to know is you need to always test on the release configuration. So you know how Xcode has debug and release? You need to make sure that whenever you do and take any of those measurements, you take them using the release configuration. The reason being, very simply, is release configuration is heavily optimized, and it's more closely to what your users would experience. It's also a good idea that you do this on your base model, on your minimum supported device. So for example, if you're targeting iOS 10, that would be an iPhone 5. If you're targeting iOS 9 or iOS 8, for all those you building mobile banking apps that you need to support, since forever, that would be an iPhone 4S. Again, the reason for that is if you start from the very minimum and if you ensure that performance works and is adequate for lower-end devices, most likely it will work for faster devices as well. Having said that, a lot of those issues that I'll explain are not necessarily tied to performance, as in your problems won't necessarily go away if your device is faster. They won't go away. They might become, I would say, harder to find because they're less likely to occur, but they're still there. So it's a good idea to do it on a base model because obviously it makes it easier for you to find these problems. So I talked about red flags and how they lead the investigation. And when it comes to memory usage, as an example, there are things like memory usage that keeps growing and growing and growing. This is a red flag. If it's growing without control, if it's unbounded. CPU. If CPU, for example, is constantly hammered, constantly busy at 100% CPU usage for a long period of time. Again, that's a red flag. On its own, it doesn't mean anything, but it leads into the investigation. It makes you want to have a look to see what's happening. So we're going to start with memory. Now, memory, very simply, it's how much you can use before you crash. We're working with devices that are constrained in terms of memory. We don't have desktop or server configurations with, terabytes of memory or tens or hundreds of gigabytes of memory. We're talking about low-end devices. And personally speaking, I find it interesting how this topic, it sort of has come back into the forefront again, this idea of thinking about memory, which obviously over the years we have stop thinking or have been thinking less and less of it. It's always an issue. Even I'm pretty sure you've used, I don't want to pick someone, but let's say it has a red tail and it's a browser, that it's quite heavily on the memory usage side. So it's still an issue to the desktop. It's only that it's even more important on mobile devices because obviously you have more tight space to work with. And this is what it looks like by today's standards. So again, we have iPhone 5. These are only this is the all of the available memory that a device has. Okay. So starting with an iPhone 5 or an iPhone 4, sorry, you can see 512. That's megabytes, going up to 1 gigabyte, 2, and 3. 3 is as much as we can get with the iPhone 7 Plus. So let's see how much 512 megabytes of memory really is. The trick with that, and something you have to be mindful of, is that not all of it is yours. For better or worse, the operating system occupies memory, other apps occupy memory. So it's not that you have 500 megabytes of RAM to yourself, okay? And to give you an example from a real-world experience that I had, because these numbers are not fixed. This is a graph of an iPhone app that's been profiled on an iPhone 4. On the left, you see what we call the baseline memory usage, and I'll come to that on the next slide. The middle one shows how much the memory usage was when it crashed, and the last one is obviously how much it's available. So you can see it's not even half when this app actually crashed because of memory usage, of excessive, I should say, memory usage. The bad news is that there's no hard limit. So just because this app crashed at this number doesn't mean that your app will crash on this number. It depends a lot, and it depends on things like how many apps are running in the background, how much, how aggressive are you allocating memory. So these are the bad news. The good news is hopefully we'll see through these slides how you can deal with these situations, as long as you have visibility of these things. And that's why I said in the beginning that it's important to have visibility. It's more about visibility. So we have our device on our side. We know the configuration that we're going to run this on. And the next thing that we do is we need to establish a baseline. So what is a baseline? A baseline is basically when you start taking measurements from. So, to give you an example, let's say you have an app that it shows photos of kittens. See, there are kittens in this presentation, I told you. So you launch the app, you go into a feed, you page through it, and you see photos. If that is the whole functionality of the app, where you really want to start measuring is the minute the app is launched. Because once the app is launched, you have established a baseline, let's say, when the user now starts using your app from. Because as he pages through these photos, memory usage will go up, caching probably involved, caching those images. And you want to basically start with whatever it is that feature adds in my memory, starting with a base. Because launching the app, you can't get away from it. You need to launch the app. The app needs to load. And there is a lot of things that go, and in launching an app, there is a lot of memory usage that is outside of your control. Things like frameworks, for example. When you have libraries, that you load. So all these things add to the memory. Or when you have, your app's binary size will add to the memory. So if, let's say, by launching the app and looking at the home screen, there's anywhere between 50 and 60 megabytes of memory usage, then this is your baseline. You start from that. That's the minimum you need to start. You cannot get away from that. And then as the user starts using the app, memory might go up to 100, 150. So it's that block that you need to measure. This is how much the feature that you've built contributes to your memory usage. So first you establish a baseline. Another example is if you're working on, let's say, an app that has a user login or has a user registration. Again, the user would go through registration. You can measure that as well. But then most likely it will end up in a home screen, in a dashboard, in a landing page, let's say, in a view which might be a tab bar that you see at the bottom. And this is where all of the functionality of the user starts from, okay? This could be your baseline, because every time the user will use your app, will start from there. So you establish your baseline, and then you measure from that. It will become more clear later as I go more through these things. The second thing that you do once you've established your baseline is you draw a trend. So effectively what you do is as you go through each feature, you draw the memory trend. Does it go up? Does it go down? Does it keep flat? This is important because, again, this gives you an idea of how your app performs. This will tell you whether there is a red flag or not. For example, this is one scenario that you may come across while you profile your app, where you have the app, the first one being when it's launched, so you have some memory overhead, going through maybe tutorials, registration, login, onto the main screen, and then your next feature, whatever that is. And this is all your app does. In this case, your baseline, you can almost say it's fixed, because it doesn't go up or down. Whatever you've allocated by launching this app, by going to where you want to go with your user and whatever it is that you offer, it's fixed. It won't go up. As long as your baseline obviously is smaller than whatever it would take to cross it, you're safe. You're not good, you're not doing spectacularly, but you're safe. And this will become clear later as well. So this is an app with a fixed baseline. So you allocate memory as you launch the app, you go through things, and then you land on a spot, and then you finish there. And everything that your user does is from this baseline. And whatever memory you've already allocated satisfies that feature that you've built for your user. The second scenario you might come across is when you have a bounded baseline. And what does that mean? It means that, again, you launch the app, you go through tutorials, you land on a home screen, and the minute you land on a home screen, your memory has dropped. So you might ask yourself, so how is that possible? How is it that the user launched the app, went through the tutorials, registered, landed on a home screen, and now I'm consuming less memory? I can give you an example. Assuming the user goes through registration once, and he doesn't need to go back to it, because they've registered, they're using your app now, what you could have done is replace this whole stack of views and view controllers that you've just used to register your user with just one screen, which is your home screen. So effectively, you've released everything that came before it, and now you're showing a home screen. So this is a scenario where your memory usage will drop slightly, or it could drop. And then you start measuring from that. So then this lower point, the fourth one that you see, becomes your baseline, because effectively this is where your user starts using the app from. It's not the previous one. It doesn't have to do with registration, because he's gone through this. You've thrown it away. This is now your baseline. And you start measuring from this. So the next point is that you see on the graph, the fifth one, is your user, I don't know, opening a map, let's say, and viewing some ATMs around here. Your memory goes up. They close this map. They go back to their home screen to see their balance and see their latest transactions. Memory should drop back to the baseline, because whatever memory you've used to show that map, you've released it, hopefully, and you're back to the baseline. And this is what a bounded baseline looks like and what it means. You're basically going from a baseline that you've established up and down, up and down, up and down, as long as you don't cross. The third one, and the worst probably, is the scenario where you have an unbounded growth. And what this means is you keep allocating memory like there's no tomorrow. That's what it means. And obviously there's a problem with that, because like we said, devices are constrained on memory. You need to think of these things. It's not infinite. And in this case, again, what will most likely happen is eventually you will reach to the crash. Again, you might debate and argue, but how long will it take for our users to crash, or what features are they going to use? And maybe they won't use these features. And you'll be right. There's no way to predict how your users will behave. But when you do memory profiling, you're not factoring in user behavior. Because the minute you factor in user behavior, it's chaos theory. You have no way of predicting it. So as long as you build a feature and it's in your app, measure it, count it against. So calculate usage per memory feature. It helps you plot these trends and establish baselines. And it also helps you identify which features are more memory hungry, let's say. So other than establishing a baseline and drawing a trend, it's good to have a pie chart. And if we say the whole pie chart is all of your memory usage that your app is using, each of the slices, it's a feature and how much it contributes to the overall memory usage. And this could be in megabytes, for example, as well. And again, this tells you where to focus your efforts. Okay? What's more important, or what's more heavyweight in terms of usage? There's also this thing called memory warnings. So I would say this is the good news, actually. So how familiar are you with memory warnings? Show of hands? Okay. So memory warnings is basically this. When your app reaches a point where iOS thinks it's using too much memory, because we said it's not a fixed point, it will send you a warning, okay? And in terms of code, that looks like a simple method that says that it's called application did receive memory warning, and you need to implement, typically in your view controller, let's say, and respond to that. So the system calls you on that method. As long as you implement, it calls you on that method. And it tells you, hey, can you release some memory, please? And it tells you, please, actually. It's very polite in the beginning. Like, it just nudges you. It's like, there's something going on here. Can you do something about it? You might choose to ignore it. The second time again, the operating system is going to come around and say, pretty please? You're really pushing it here. I don't want to do anything nasty. And the third time, you'll crash. So the OS gives you chances to respond to those memory warnings. And the one simple way to think of memory warnings and how to deal with them is basically release memory that it's no longer used. That is the most basic thing. So for example, if you are, I don't know, if you've allocated some, so let's say you fed something from the network, you keep it in memory, your user has gone off to some other screen and is no longer looking at this thing, release it. Of course, you need to think that this is going to be recreated at a later stage, but this is fine. You will get your chance to recreate. So anything that you can recreate from the server, it's fine. You can release it. You can recreate it. Anything you can recreate from reading from the drive, it's fine. You can release it. You will recreate it. Things like caches. You can choose to, as you load things from the network, you're probably doing some caching. So you cache responses. Again, if your cache is unbounded, if you keep caching things without really thinking of how much memory they use, you'll get a warning. That's okay. Release that. Build your cache again. The other thing is abandoned memory that you have to be mindful of when it comes to memory usage and profiling. And I see this, there's a misconception between what abandoned memory is and what leaks are and what retain cycles are. So there's a lot of misconception around this. Abandoned memory, it's not a leak in the strict sense. And what do I mean by that? Abandoned memory is memory that your application is using a referencing, so you're still referencing that memory, but you're no longer using it in your app in some meaningful way. And again, I'll show an example later what this means. So your memory is still there. You've allocated memory. It's lying around, but it's just that you're not using it for whatever reason. And the way to identify problems like this, of memory where it's been abandoned and it's been referenced, or one way at least, is to use what is called generational analysis. So, show of hands, how many of you have used instruments? Okay. How many of you have profiled for memory usage? Okay. So I should watch now what I'm saying because I don't want to be embarrassed. So let's see how that works. And I have a little video here. I'll play it back in a minute. So you launch instruments, you choose allocations, and on the right-hand side, you'll see a table view. So this is just a simple table view that the user can scroll and go through rows. So you choose allocation, and one thing to note is that as I start going through this, you'll see memory being allocated, and you'll see the graph and the trend that I talked about. And there is this thing called mark generation. And when you tap that button, it takes a snapshot of whatever objects are currently in use. And you can also see the memory usage as well once you hover. So it takes a snapshot of whatever memory usage you've already used. These are objects, so it will be strings, it will be views. And then you can see as we now scroll through the app, you've taken your first generation. When you first launched the app was stable, memory usage was stable. You use the app. You use it once, you take another generation. So you mark that. You see usage has gone up. We have a second generation at the left. You use it again. You mark again a third generation. So every time that you use the app, the feature, which is scrolling through pages, you mark a generation. And that captures whatever memory you've used up until that point. And then at the end, you'll see that if you expand those, can you see it at the back? Yes? So if you expand in those generations, you'll see references of things. And the most important thing is that every time you snap, you mark a generation, it keeps track of whatever instances were created during that time. Okay? So whenever you mark generation, it takes a snapshot of whatever instances were created between your last generation and the minute you mark it. Okay? So what this means is between the first launch of the app and the scroll, there's been 66 on the right images that have been created. They're still around. They haven't been released. They're still around. And on the second swipe that we did, we marked generation again at the end, and we see that we have now 58 images that have been created. Okay? So this tells you what's been created and still around. It hasn't been released, it's still around, every time you mark a generation. Okay? And you saw the trend as well as memory went up. So this is bad, obviously. This goes back to the third scenario that I talked about, where you have unbounded growth. Memory keeps growing up and up. And you can even see the usage. It's like almost 200 megabytes. Do you see that? Yes? I'll take it you're fully immersed into the talk rather than sleeping. So 200 megabytes of memory. So let's see how we can identify who's creating these allocations and how can we solve this. Because obviously we've seen the trend, it looks bad. We've marked generations to investigate. And the thing you do is, one way is to look at the stack trace. So, and find who's causing these images, who creates those instances, and look at the code. Again, keep in mind that you don't need to have inside knowledge of the source code. You could have equally done it on an unknown code base. Because what you do is you look at flags, you look at graphs, you look at memory going up. You mark generations, and you see memory usage. And you'll see now how this can lead you into the source code. So if you go to one of them and you select it, you'll see all the references that have been created. And then you just choose one, because most likely all of them are created at the same spot. And then on the right, you have this extended detail, which basically gives you a stack trace. And then you can double click, and assuming you have the source, you can go straight into the offending code. Okay? Was that good? Can I get a round of applause? Thanks. So you see how you don't need to have this inside knowledge of the code base and how it leads you. It even helps you learn about the code base and how the code base works. The next thing where unbounded and when you can have memory that grows without control or without you noticing it, and it's not about, again, it's not about a leak, it's about unreferenced memory. It's still memory, it's still around, but you're not using it, is by debugging the UI hierarchy. Question, how many of you have used this debug, the UI hierarchy, or you've used tools like Reveal, for example? Okay? So the idea is that you have a running app, and while your app is running, you pause it. And the system takes a snapshot of all the UI elements and the UI views. And then you can observe those views. And we'll see how that happens in a minute. So this is just a storyboard. This is what it looks like, our UI view hierarchy. We have a simple navigation controller with 3 view controllers as we present them. And we're running the app, as usual, on the simulator. For this case, by the way, we don't need instruments. We're just doing it all from Xcode. And then at the end, we press down and we show this model view. And then if we go to the debug menu, you can see this view UI hierarchy. And then, you can see how there's actually a view behind the scenes, which obviously you couldn't see. Okay? So this gives you a 3D overview of the view. And if I go and change the source code, you don't have to worry too much about it, just to show you how now it's been fixed and how this thing won't be behind it. Again, you launch, you go to the debug, you go through whatever process you want to go, view UI hierarchy, you have your snapshot, you press the button and you go to 3D mode, and then you can simply expand this and see behind. So there's nothing behind again. So this is a very simple way of looking for abandoned memory. Memory that you're no longer referencing, you're no longer using, but you're still referencing. The user, if you look at the simulator, at the screen, at the UI, the user has no means of going back. So really, there is no reason to keep this view in memory. Linked memory. This is probably what most of you must be familiar with. So linked memory is memory that it's not referenced directly from your app. It's not in your object graph. And it's not used. And this is typically created by reference cycles that you might be familiar with. So how many of you know what a reference cycle is? Okay. So a reference cycle, to put it simply, is when you have two instances, two objects, each referencing one another. So let's say you have a view controller and an object foo. And this foo object has a delegate. And you've assigned the view controller as the delegate of foo. So not only the view controller references foo, but also foo via its delegate references the view controller. Now this isn't a reference cycle in itself. How you get a reference cycle is if you have your view controller referenced by your window, so you have someone else holding on your view controller, which holds on your foo object, which references back to your view controller. When this thing goes away, when this reference goes away, and we'll see an example, all of a sudden, your view controller that was holding into your foo is no longer referenced by the window. So it's by any means it's gone as far as you're concerned. It's not on the window. It's not presented. It's still alive, but it's not on screen. But because this reference is now gone, you have a view controller that holds on an object, and the object holds on its view controller. And there is no way to tell what goes next, because they both reference them, and no one else calls the shots. No one else says when these things should go away. And this is a reference cycle. And this is when you get linked memory. Again, let's look at an example. So we have a simple view controller presented in a navigational pattern. You press next to go to the next slide. You go back. We'll do this a few times. And then again, from the debug menu, you see view memory allocation. And if you click on the left, you'll see how this is now a retain cycle, a reference cycle. Because these are the only two objects involved. And you see no one else is playing any part in this. Only the linked view controller and the foo. Okay? And again, you can see that straight from within Xcode. You don't need instruments. Just a small note, this is Xcode 8. So whoever works in the banking sector don't get to play with this, because you have to maintain legacy apps. Yes? So the way to solve this is obviously to reference it as a week. And if we go back to this video, you'll see that the delegate was actually not identified as weak. So now we're going to change it. We're going to run it again. We're going to play again a bit, back and forth, to see if we get the cycle. and it's gone. Okay? You don't see any cycles there. It's only the view controller that is currently on screen. One other thing which is not, it doesn't necessarily have to do with performance, but it definitely has to do with memory. And it has to do with bad access memory. And this is basically a typical case where you try to access an instance, you try to reference, and the memory has been deallocated. The reference has been deallocated and it's gone, but you still try to reference. And one typical way to get into this state is if you're using closures or blocks, let's say, in Objective-C. Because you capture a reference of whatever it was for a later, to later access it and do something with it, but maybe that view controller, in this case, it's already gone. And we're going to see how, again, that works out. So again, we have our typical setup of a navigation with two view controllers. And you go in, you go out, the view controller has been deallocated, the blue one, and then hopefully we'll get across. And you see this abort, retain, unowned, and even if you look at the stack trace, you can see how we've captured self in unknown. And if we change it to weak, which is, it forces you to think of optionals, you can do this optional chain of referencing something. So in this case, if it's null, then the call won't be made. It won't try to access this reference. So you're safe. And I forgot to ask, how many of you are using Swift, or are you familiar with Swift? Okay. At least half of you know what I'm talking about with optionals. And this is nasty. This is very, very nasty, because it can bite you when you don't expect it, because it's asynchronous. Because you saw, like, the view controller, the blue view controller, which is responsible for the crash, was long gone. And the user is off to looking something else, looking photos of kittens. And now the app crashes. So, and then you try to debug this and you ask your user, so where were you when that happened? Oh, I was just looking at pictures of kittens. But that's impossible. Like, you can't crash on when you look at kittens. So this is why it's nasty. You know, it's timely related. And there's a lot of things that might be involved. But hopefully it should be easy to fix in most of the cases. And again, this is, by the way, this is something that you can easily catch with either pair programming or code reviews, which I'm guessing every one of you does, right? So what are the risks? Why did we spend the last 20 minutes, I think, because I've lost track of time. 20 minutes? More? Okay. Talking about high memory usage. Well, because your app might be terminated, and this is a bad experience. It sucks. Using your app, and then you're in the middle of something, it crashes. And it's not only that it degrades user experience, but it's also, it might be critical. You might get data corruption. You might get stale data. You might end up doing something in a critical application that while in the middle of doing something, your app crashes. So you have to deal with these issues. This can be very, very serious issues. So your high baseline, like I said, it's okay that you have a fixed baseline, but it also, you have to think that it puts a constraint, because obviously if your baseline is too close into the crash, then it puts constraint on anything that you want to build on top. So eventually you will have to think about this thing. Or either because you won't be able to build whatever you want to build, or because you have to take huge compromises on what you're going to build. Like high resolution pictures of cats. You'll only be able to show slow resolution. Your app can still be terminated in the background. And this is something that you typically manifest for the user as in, okay, I'm trying to launch this app. Oh, shit, I have to still like go through registration. I still have to go through login. Because your app probably crashed or was terminated, wouldn't crash, was terminated while in the background. Other apps are getting killed. How many of you have blamed, I don't know, Facebook because your other apps are getting killed? So what do? You bring the baseline down. That's the first thing. You bring the baseline down by reducing image sizes, by reusing memory. So reuse memory as much as possible. You release any unused memory. So any memory that is no longer used, you should release it, and you should make sure that you return to the baseline. If you're not returning to the baseline, you're leaking, okay? Or you have unused memory. So you should always return to the baseline. Reuse memory, so don't allocate more. And next, CPU. So how much time do I have left? 10 minutes, we're good. So CPU, it's all about getting things fast, getting things done fast and responsive. And what is responsiveness? What do we mean by responsive? Like, one thing is that it needs to be responsive to the user's touch. So we don't want our users dragging the fingers and then 2 seconds later the screen follows. So it's all about being responsive to user touch and user input. And it's also about being responsive to user as a result of a user action. So for example, when the user, let's say, taps to log in, you want to be as fast as possible going to the next screen. You don't want the user to just sit there and wait, okay? So this is one example where I've actually tapped now the next button twice, and you can see how it quickly went back. Let me do this again. So this is an app that will show you what it feels like from a user's point of view when there's something wrong with your CPU, with your processing, with how you process data. And it's a simple navigation. You press next, you go to the table view, you scroll through this, you go back, you tap next because you're like, oh, I forgot something, and it fails. And then all of a sudden you get 2 pushes because the OS at this point registers those touches and responds to them. And now I've actually scrolled. It's not frozen. The video hasn't finished. The scrolling is actually frozen because there's something going on, and now it starts again. So this is how these things manifest from a user's point of view. So in this case, it's about UI lag and not responding to touches. And you would use a time profiler for this. Again, from Xcode, you can press Command-Shift-I, and you select the time profiler, and you start recording. And again, you'll see, what you see at the top is basically usage of CPU over time. And below, you see the stack trace. So you see the main thread, for example, there. And in this case, clearly, the main thread is kept busy because the UI doesn't render anything, doesn't respond. And if we expand this, we'll see how on the left, you see how on the left it says 2 seconds? Yes? So on the left where I've highlighted, you see 2 seconds. Basically, this is how long it felt, it actually is for the users. It actually took for the UI to update. It took 2 seconds. And this is something there's no dispute to that. It's not a matter of, oh, I'm using it, it's not slow for me or whatever. You've proven it by looking at that. Your main thread is busy for 2 seconds. 2 seconds means that the user cannot touch, cannot do anything on the screen for 2 seconds. And yeah, we keep talking about this idea of 60 frames per second. And this is just to give you a perspective of what this means. 60 frames per second means that every 17 milliseconds, the OS needs to process a frame. Let me say that again. For each frame, the OS needs 17 milliseconds. And we've just blocked the thread for 2 seconds. So if it was less, if it was closer to, I don't know, 50 milliseconds or 30 milliseconds, 30 milliseconds probably means you're losing a frame every, you're losing 2 frames. if it's 40 milliseconds processing time. You're losing 2 frames every time, so it stutters. You would see it like going like this. There's also user waiting time when it comes to CPU. So when the user is waiting for something to happen, and the UI has nothing to do, you're just waiting for the server. And this is fine. This is fine. There are cases where you need to talk to a server. The users understand that concept by now. They understand this relationship of an app waiting to go some results and return. They get that. But what you need to, what you should be doing is showing activity spinners, communicating them to the user. And in terms of performance, you can think of, you need to know the limits where the user starts to get annoyed about these things and how fast things should be. So one simple way to think of it is anything that lasts 0.1 second to the user, it's instant. Okay? So that's 100 milliseconds. To the user, it's instant. He won't be able to tell the difference. From a second upwards, up until 10 seconds, the user is waiting. He understands that he's waiting. So obviously, you shouldn't tie operations like this one of 2 seconds on the UI. But it's fine if you tie them to a network call. The user understands that he's waiting. Anything above 10 seconds, then obviously it's bad. Again, graph how much you spend per functionality, and try to stay idle as much as possible. So let the CPU rest, because if you let the CPU rest, that means you're saving on battery, for example. Or it means that you don't have to worry about the CPU and what it's doing. You're just letting it rest. And that's an example of how that would look when you have, oh yeah, this is a timer. Sorry, I forgot about that. Halya, how many minutes do you have? Do you have 4 minutes or something? Or? Yeah? Have I eaten all of their questions?
We are already like 10 minutes.
Over? Oh, due to me? Oh, that's great. Let's run. You'll catch me after the break for more, for questions. But yeah, basically, I'm going to show this. This is about a timer. So this is a timer that hasn't been dialogued. So the time profile in instruments can also tell you things like timers, because you see there's a pattern. There is some sort of a spike that you see at the top, which seems to be like in a schedule, in an interval basis. And even if I've escaped, even if I've dismissed the view controller, you can still see all these spikes. So they're still going. And again, this tells me that most likely there is a timer that it hasn't been dialogued. And you'll see it at the end at the stack trace. You can zoom in on one of those things, and then go through the main thread, expand all the calls. And again, typically from the right, you can see the stack trace, and you'll see that the timer has been added and hasn't been deallocated. Risks, again, why high CPU usage is a bad thing. The main thread is busy, which means unresponsive to touch. You also miss opportunities to respond to memory warnings, like I said before, because memory warnings, you get callbacks on the main thread. So if your main thread is busy, you won't get the callbacks, and the next thing you'll crash because you won't have chance to react. It degrades user experience, so it doesn't feel smooth. There is this lagging, this user waiting. But even though you're not on the main thread, experience might still be affected because you're keeping the CPU busy regardless. Like there's so much CPU usage going on in the background thread that it doesn't leave any room for the main thread to work on things. And you have the typical battery drain. What to do? So offload processing from the main thread on a background thread. Postpone processing when required. So rather than doing it on the spot, on demand, do it later when being lazy about things, computations, doing maybe in the background again, but at a later stage. Remember that 2 cores effectively means 200 CPU usage. So partition the work between threads. and find what's keeping your CPU busy. Generally speaking, some tips and tricks to finish off. Don't tie the user interface to processing. So it's fine to have a button that the user taps. You show the spinner, and the user waits, and then you move on. But it's not fine if the user taps, waits for 2 seconds, then the button highlights to respond to the taps, then you go to the next, because this affects your UI. Use spinners. Spinners are fine. They're not a bad thing. So we all want things to be fast, and I've had designers telling me, when I ask them about spinners, they tell me, oh, but I want this to be fast. It will be fast. I'm like, yes, but. So don't be afraid of spinners. Another very important thing is the did finish with launching options. This is your entry point to the app. Make sure you're not doing too many things. 400 milliseconds is a good target. If it takes more than 20, you're killed already. But even if it takes 5 seconds, your user is like sitting there waiting for a splash screen on a fancy animation that, again, you've decided, you've thought it's a good idea. Launching the app, it's not about pretty animations. It's about getting to the user to do and use the app as fast as possible. In terms of memory, application did enter the background. Use it to release resources and persist state and stay low. Just because you're now in the background doesn't mean you still don't have to think of memory. You do, because if someone else is in the foreground, guess who the OS is going to choose to kill next? Not the first one, you. Measure performance on IB actions, things that relate to the touch, any handling, completion blocks. And finally, try to put this, it may sound like a lot to grasp right now, and it is a lot to grasp, but once you get the hang of it, it's very easy to have it on a schedule and to have it as part of your development workflow and as part of your release schedule. Like for me, it takes now, I don't know, half an hour, maybe an hour for the first pass to just have a reference, and then it's like that. It's like you go through these things you know already, you don't see anything, then you're gone. It's like, I don't know, tens of minutes, 10 minutes, 15 minutes, it's on every release. It's not too much. And keep a record of your measurements so you can compare and contrast. So have a record, have a history to see how your app performs. And go forth and release, being confident, knowing the risks, at least knowing what's happening. Thank you. Oh, one more thing.
Yeah, so I want to ask if you see value in getting this kind of information from release environments. So, do you use New Relic or similar? And do you think the data you can get from a production environment or release environment where many things are running on the mobile app of the user make any sense? Or it's better to try to isolate them all during, staging or development?
I would say if you try to do this stuff live, then you're making your life harder. Because there is a lot of things that are outside of your control, like network conditions or whatever apps your user is using, or user behavior even, that it's going to make it very, very hard, assuming you even get that information in, because that's another thing. How do you get that information? How do you know that your apps are not crashing and you don't know about it? Well, we had bug sense, was it? But there are other things, like you saw, that they're not necessarily related to crashes. There are other things that it's hard to get. So the short answer is no. I think you'll be making your life much, much harder if you were to do it on the real world. But having said that, I don't know how much progress it's been done on that front to how clever the tools are or how much you can get.